So let's take a look at a couple examples with regard to potential energy and kinetic energy. So we said that potential energy is stored energy, and there's different ways to store that energy. So potential energy is stored energy that has the potential to do work. And one way is that it has the potential to do work with regard to the force of gravity. So for instance, as this person threw up this ball, when the ball is in this position, it has basically a potential to do work. It has potential to have energy based upon its position here. We'll call this H. Okay, so here actually, as it's high in the air, it has lots of PE, potential energy. All right. So now we said that then actually as it falls, and we kind of see it having kind of an arching movement here, but as it falls it's going to go faster and faster, and so actually we definitely have motion. Its motion is going to increase as it's going to go faster and faster and faster. So actually it's going to pick up kinetic energy. Kinetic energy is associated with motion, okay, is going to increase as it falls. Specifically, right before it impacts, it's going to have the most KE, and it's going to have the least potential energy, least PE. Why? Because it doesn't have anywhere to fall. Okay, its H has gone down. Okay, so that actually is, in a nutshell, converting potential energy to kinetic energy, right? So we actually have this other sort of potential energy and kinetic energy conversion going on, and this in a couple of chapters when we talk about our solar system, we're going to actually talk about how our solar system, which ended up being, you know, the sun and the planets that orbit the sun, and there's all sorts of star systems out there that did the same way, that formed the same way, actually started out as a big old nebula. And I've introduced the term nebula earlier in the course, basically a gas cloud. So now that is going to turn into our solar system, okay, over like 100,000 million, 100, it'd be 100 million years, 100,000 years. I'll have to double check that. But my point is, when it's nice and big like this, it has what we call lots of potential energy right there. Lots of potential energy. It's nice and big. Now, the cloud collapsed, and there's different ways to get a cloud like this to begin collapsing, okay, to ultimately get material in here that's going to become our sun, and then actually material in orbits that's going to become the planets. But the cloud became stimulated, began condensing or began contracting, okay. As it became smaller, my point here is that it has less gravitational potential energy now. Now, what we found is that that energy needs to be converted to more kinetic energy, just like we saw a minute ago with the ball falling down. So here we have more kinetic energy, and actually that means increase temperatures. Okay, and as you may know already, actually in order for a star to turn on, we need to have a certain temperature in the center of the star. In order for our sun to turn on for the first time some 4.6 billion years ago, it needed to have a certain amount of thermal energy, a certain critical temperature. So that was a key player, the conversion of potential gravitational potential energy into kinetic energy. So speaking of high temperatures in our sun's core, actually what stars are doing, like our sun, okay, actually they are very similar to what was done in a nuclear hydrogen bomb. They are taking, we'll talk more about this, but they are taking atoms, okay, and actually in the case of our sun, it's hydrogen atoms, smashing them together and getting a heavier atom. Okay, I know it's like much more complicated than that. And in doing so, if you were to weigh this, I'll call this M1 and I'll call this M2, okay, it has lost mass. lost mass. Okay, and it has lost mass, and that mass is converted to a lot of energy. Okay, according to Einstein's equation. So actually, this is let's see, energy and matter are collectively conserved, but actually, if the conditions are right for nuclear fusion, such as this, a small amount of matter, okay, can be converted into a large amount of energy. I say a small amount of matter because actually this, I don't know if you recognize this c, did I tell you what that? C is the speed of light. And the speed of light is a large number. This down here says 300,000 kilometers per second. So that's a lot of energy. And so, of course, then the example I have here, not the controlled nuclear burn that we have in stars, but nuclear bombs. We have both fusion bombs, would be a hydrogen bomb, and fission bombs, which would be a uranium bomb. But what they're doing in common with the sun is they are converting a small amount of matter into a large amount of energy.